Here's a look at predicted R-square. The least squares method optimizes the results to develop a model that fits the data in the sample. No other model, basically a set of regression coefficients, will have a higher R-square. R-square is the proportion of the variation in your dependent variable that's explained by the model. You cannot really evaluate how well your model performs with the same data used to develop the model. You need to use new data that was not used to build the model. And invariably, the model will not do as good a job with new data. You need to cross-validate the model with new data to see how well it performs in the real world. One way to cross-validate predictive models is through leave one out cross-validation, LOOCV, pronounced LOOCV, and the predicted R-square. Here's the concept with LOOCV. I start this example with a full data set. Here we have 8 observations and 2 independent variables, x1 and x2. The first row is removed from the data set, and a multiple regression model is developed using observations 2 through 8. Observation 1 is not used to build a model. The model is used to predict y for observation 1, with x1 equaling 28.0 and x2 equaling 18 for new data, used to predict y. The predicted y is compared to the actual y for observation 1 of 12.4. You find the squared differences between the two, called the squared residuals. Next, observation 1 is returned to the dataset, and observation 2 is removed. Now a new model is found using observation 1 and observation 3 through 8, but not observation 2. It's being held out. The model is used with new data, x1 equals 28 and x2 equals 14, to predict y. The predicted y is compared to the actual y value of observation 2 of 11.7. You find the squared differences or squared residual between the two. This process continues until all of the observations have been held out one time. We calculate the squared residual for each of the subsamples and sum the results. This produces the PRESS statistic. PRESS stands for Predicted Residual Error Sum of Squares. The predicted R-square is found by 1 minus PRESS divided by the sum of squares total. This predicted R-square gives us a more realistic idea of how well the model will perform with new data. It's also used to compare one model to another. The model with the higher predicted R-square would be preferred. On this slide, I show how to use the OLSRR package to find predicted R-square. Line 1 loads the package. Line 2 performs the regression with weight and horsepower as the independent variables, and miles per gallon as the dependent variable. And it stores the regression output in an object named model. Since this object holds the results of an LM analysis, that is a linear model, it's called an LM object. Line 3 uses a function from OLSRR. The function name is OLS underline PRED underline RSQ, and the name of the LM object in parentheses. The R-squared from regular regression, not LOOCV, was 0.8268, and the interpretation of this is that the model explained 82.68% of the variation in miles per gallon. The predicted R-square, on the other hand, equals 0.7811 rounded. Predicted R-square is a more realistic estimate of how well the model will predict new observations. This is important because adding new variables to a multiple regression model is easy, and it always increases R-squared. So you might be tempted to keep adding variables to the model. But this can quickly lead to overfitting the model, making the model too complex with too many independent variables. A key benefit to the predicted R-square is that it can help you find models that overfit the data. If the predicted R-square goes down when you add another variable to the model, this indicates overfitting. An overfit model is too complex, and it actually starts to model the random error in the data. Thanks for watching, and please let me know if you have any questions.